All right, welcome back. Today, we are diving into one of the most powerful detective tools in all of science. It's called spectroscopy, and it's this incredible method that lets us understand the universe on a molecular level, even from millions of miles away. I mean, think about that for a second. It really sounds like magic, doesn't it? How could we possibly know the chemical makeup of things we can't reach or things that are way too small to see? Well, this was a huge mystery for centuries, and the answer scientists came up with is nothing short of brilliant. And the secret, the key to all of this, lies in this fantastic idea of a molecular fingerprint. So in this first part, let's unpack exactly what that means. At its core, spectroscopy is all about the conversation between light and matter. See, when light shines on or passes through a substance, that substance leaves its own unique mark on the light. And by analyzing that mark, we can basically work backward to figure out exactly what we're looking at. This right here, this is the core concept for this entire explainer. You have to get this. Just like no two people have the exact same fingerprint, no two molecules interact with light in the exact same way. That unique interaction creates this fingerprint, and spectroscopy is the amazing tool we use to read it. So if molecules have these fingerprints, what language are they written in? Well, the answer is light. But to really understand this language, we first need to appreciate that light itself is way more diverse than you might think. We tend to think of light as just, well, what we can see, right? But that is just a tiny, tiny fraction of the whole story. Light is a form of electromagnetic radiation, and it exists across this vast spectrum of different energies. And this image just illustrates that range perfectly. I mean, look at it. On one end, you have super high energy stuff like gamma rays and X-rays. Then on the other end, you've got these long, low energy waves like radio waves and microwaves. And squeezed right there in the middle is that tiny, beautiful rainbow of visible light that our eyes can actually pick up. The type of light is going to determine exactly how it interacts with matter. Okay, so we have our molecular fingerprints, and we have the language it's written in, light. Now let's look at the main event. What actually happens in that moment of interaction when a photon of light slams into a molecule? Well, it all just comes down to energy. Think about it. Low energy microwave radiation, it has just enough juice to make a molecule kind of spin or rotate. A little more energy from infrared light doesn't make it rotate faster. Instead, it makes its chemical bonds stretch and vibrate. And that high energy UV or visible light, whoa, that packs enough of a punch to literally kick an electron into a higher energy state altogether. This diagram is such a great way to picture it. Think of a molecule's energy levels like a staircase. It starts on the bottom step, its ground state. A microwave photon can give it just a tiny nudge up one of the small rotational steps. An infrared photon can push it up a bigger vibrational step. And a UV photon can launch it way up to a whole new floor, an excited electronic state. Now the key here is that these steps are fixed. A molecule can only absorb a photon if it has the exact amount of energy needed to make one of these specific jumps. It can't land in between steps. Okay, so we know molecules absorb very specific energies of light, and this is what creates their fingerprint. But how do we actually read it? Well, there are two main ways, and they're basically two sides of the same coin. Absorption spectroscopy is kind of like shining a bright white light through a stained glass window. You look at the light that makes it out the other side to see which colors got blocked, which colors are missing. Emission, on the other hand, is the opposite. It's like heating up a piece of metal until it glows red hot. You're not analyzing a light source passing through it. You're analyzing the light that the object itself is creating and giving off. The setup for absorption is really quite simple. You've got your initial light source, we'll call that I0, which you shine through whatever you're testing. Then, a detector on the other side measures the light that makes it through, which we'll call I. And the difference between what went in and what came out, that tells you exactly which wavelengths the sample ate up. So, this is the crucial point. The shadow is the message. The specific colors of light that are missing create this unique pattern of dark lines, almost like a barcode. And that pattern, that barcode, is the molecular fingerprint. It lets scientists identify the substance with total confidence. Now, with emission, you start by pumping energy into a sample. You could use heat or electricity, whatever works. This kicks its molecules up to those excited states we saw on that staircase diagram. But they're not stable up there. They can't stay there forever. So as they fall back down to their comfortable ground state, they release that extra energy as photons of light at very, very specific colors. And capturing those colors gives you the emission fingerprint. And now, for the final piece of this puzzle. Identifying a substance is amazing, right? But what if we need to know how much of it there is? This is where we go from just identifying to actually measuring, from qualitative to quantitative. And this is such a critical question. It's used in everything from medical diagnostics to checking for pollution. I mean, knowing a pollutant is in the water is one thing, but knowing its exact concentration is what tells you if it's actually dangerous or not. Luckily, the logic here is super intuitive. First, just think about adding food coloring to a glass of water. The more drops you add, the higher the concentration, the darker it gets, right? It absorbs more light. Simple. Second, if you look through a swimming pool from the side versus looking down from the top, the longer path the light travels through the water also makes it look darker, more like it's absorbed. These two simple ideas are the entire foundation of what's called the Beer-Lambert law. And this simple but really powerful equation puts it all together. The Beer-Lambert law. It says that absorbance, which is A, is directly related to two things: C, the concentration of your substance, and L, the path length the light travels through it. That little epsilon symbol is just a constant, specific to the molecule. It's basically a rating of how good that molecule is at absorbing light. So by measuring the absorbance, we can use this little formula to calculate the exact concentration. It's amazing. So in a real lab, how do they measure that absorbance? Well, they generate a graph just like this one. They measure how much light the sample absorbs at all these different wavelengths. And the very peak of this curve, that's called lambda max, is the sweet spot. It's the one wavelength where the molecule absorbs light most strongly, which makes it the most sensitive and reliable point for getting an accurate concentration measurement. And that's really the power of spectroscopy. It's like a universal translator that turns the simple act of light interacting with a substance into this incredibly rich stream of information, telling us not only what is there, but exactly how much. I mean, this is a technique that has revealed the chemical secrets of distant stars and the fundamental building blocks of life itself. It just makes you wonder, as our instruments get more and more powerful, what other invisible secrets are just waiting out there, ready to be revealed by their own unique fingerprints of light?